Sure.
Yeah. Okay, so Dan's going to talk to us about non-commutative tensor triangular geometry and applications.
Oh, okay. Yeah, so I would like to first thank the organizers, Scott and Kimona, for the invitation to speak. It's really nice to be able to talk on this work that's ongoing. It's been going on for a while with various co-authors. All right, so I'd like to first start. Oops, let me see if I can get these slides to advance here. Uh-oh. Let's see, how do we advance these things? Click on one. Will it work? It's not working either. I've tried those too. Oh, there we go. All right. Okay, so first of all, I'd like to start with some general references. These are sort of the foundational pieces in the literature. So the first piece is the beautiful paper by Paul Balmer, who started off this subject. So the big idea that Paul introduced was that there's geometry inside the categories. So you have an abstract and algebraic category, but somehow there's some geometry inside. And he actually was able to sort of extract that geometry from the category by using various techniques. Now, this has been sort of expounded upon by a work by Benson, Iyengar, and Krause in a monograph printed by the Oberwolfach seminars. This is very reader-friendly, and this is actually how I sort of learned the subject. So if you're a student or postdoc kind of getting into this, even a faculty member, I would recommend the second reference too. And so, you know, a lot of this foundational work is due to Benson, Carlson, and Ricard, Benson, Iyengar, and Krause, with Petsova, Hopkins, Niemann, and various other people. All right, so now more specific references. So this is the work that I'm actually going to speak on today. So the first part is joint work with Brian and John Kujawa. So what we did was we applied the work in Vic and also Paul Balmer's work to actually extract geometry for these superalgebras and also for quantum leaps. And then with Yakimov and Bashaw, what we did was we extended Balmer's theory to the non-commutative case. So when the tensor product is not commutative, and this was actually to sort of mimic things in non-commutative ring theory. And it turns out by doing so, you're able to actually get a richer theory involving two types of spectra. So I'll actually describe that later on. Okay, so what I'm going to do next is I'm going to ask you, I call it the question of the universe. All right, so we all are Lie theorists, and I'd like to know, like, what you think of the nilpotent cone. So why do we study the nilpotent cone in representation? Why does it arise?
The shadow of the cotangent bundle between the differential operators on the flight, right?
Okay, so that's good. I mean, but how does it connect to representation theory?
Well, that's one reason. Well, it does, but because differential operators on the flight, right, are connected to the modules. That's connected to like the stuff that my advisor David Logan does a lot. Right. So that's why he's interested.
Right.
There's many other reasons, I'm sure.
That's a good reason. So really, the point is that the nilpotent cone is really built into the situation. And so what I'd like to do today is actually show you that it really is built in terms of the tensor triangular geometry. All right, so what I need to do is I need to introduce three concepts. So the first one is the concept of a tensor triangulated category. So these are triangulated categories with a tensor product structure. So for Lie theorists, you may want to think about representations for the quantum group, for example, or for complex semi-simple Lie algebras. Okay. And then there's a geometric object, and we're going to study these. These are called Zariski spaces. So Zariski spaces are things like spec of a ring. Okay, but we'll also enhance Zariski spaces using group actions too later on. So we'll be able to think of it as a stack. And then finally, we need a bridge that goes between tensor triangular geometry, tensor triangulated categories, and Zariski spaces. And you can imagine this is what's called support data. So support data is sort of like a support theory that takes objects in the tensor triangulated category and assigns it like closed sets in the Zariski space. Okay, it'll actually be more enhanced than that, but that's the way maybe you should kind of think about things. Okay, so let's start with triangulated categories. So I'm going to extend the definition a little bit to monoidal triangulated categories. So we have a triangulated category, and we also have a monoidal tensor product. So we're not going to assume that this tensor product is commutative. So an example maybe one should think about is like if you take a finite dimensional Hopf-algebra. So you can make the tensor product of two modules into a module, but M tensor n need not be isomorphic to N tensor n, for example. So that's an example of a monoidal category where the tensor product is not commutative. And so we want this set up so we can actually study things like finite dimensional Hopf-algebras. And in fact, that'll be my sort of first example. So you take a finite dimensional Hopf-algebra. So I've actually described the monoidal structure for you. So how do you get a triangulated structure? Well, it turns out that if you take a finite dimensional Hopf-algebra, then projective modules are also injective, and then you can actually create the stable module category for this category of finite dimensional or a finite dimensional Hopf-algebra. If you take the finite dimensional objects, you get the compact part of that category. That's called K of C. And then you could also take the infinitely generated modules too. So that's big ST mod. Okay. All right, so this will be kind of one of our main examples. Now I know people like derived categories, so let me give you a situation with derived categories. So here the tensor product is actually commutative. So you take a commutative Noetherian ring, and then you take the bounded derived category of finitely generated projective R modules. Okay, so that forms the compact part in the category, and then you take the derived category for the other part. And it turns out that these K, C, and K are also examples of triangulated categories. So we'll actually look at this example later on to recover the spec of a ring. All right, so what's the philosophy in this game? Well, the philosophy is when you have a monoidal triangulated category, you want to treat it like a ring. And you want to use the tensor product like the multiplication in the ring. So when you think about it that way, then you could actually create ideals, and then you create prime ideals, and you could do everything you kind of want, as long as you sort of do some technical things, which I'll talk about in a second. All right, so what's the most naive sort of definition? Well, it's the definition of a tensor ideal. So you have a triangulated subcategory such that if you take M tensor n inside of I, then, sorry, M tensor n is inside of I, and N tensor m is inside of I, for all M and I and N and K. So it's just a standard definition of ideals. All right, so this may come up, I would assume this will probably come up next week also in John Carlson's talk. So there's the idea of thickness. So we want the ideals to be closed under direct summands also. So they're closed under direct sums, but we also want them to be closed under direct summands. So when it's closed under direct summands, the ideal is called thick. And then we want two notions of primeness. So the first notion is what I call object-wise primeness. So if you take two objects and you tensor them together, and if it's inside this ideal, then you want either the first object or the second object to be in that ideal. Okay, so this notion is called completely prime, completely primeness for our TTC or MTC, M delta C. But we need a new definition. We need a definition where we actually tensor ideals. So we say that an ideal is prime if when you take the tensor product of two ideals, and if it's contained inside that P, then one or the other of the ideals is contained inside of P. Okay, so it turns out that this notion of ideal-wise tensoring product is the new idea that was introduced in NBY. This was also due to Braun, Krause, and Solberg back around 2007. So they defined this notion also, although they just defined it kind of formally and didn't do so much with it. So, but it does appear in the literature at that time. Okay, so now that we have the notion of primeness, we want to define the notion of a prime ideal spectrum. And that's what Paul Balmer did. All right, so this is kind of a standard definition. So you take the set of prime ideals and then use topologize. Okay, so you topologize it using like a Zariski type topology. All right. Now, there are various spectra that you can actually define. So we have this one for the prime ideals, but you can also define the ones for the completely prime ideals too. All right.
So did Balmer, so you were saying the prime ideals is the new notion, but Balmer is dealing with the prime or the prime? Right?
With the completely prime ones.
So Balmer did the completely prime.
That's correct. Yeah. Yeah. So that was, and it turns out that when in the commutative case, they actually agree and prove that. But in the non-commutative case, they need not. And that's an important point because you can differentiate the two, then you could actually solve problems by making that distinction. Okay. All right, good. All right, so you have the notion of completely prime spectra, and you have the notion of prime spectra, and then you have an inclusion with the two. All right, so now I just want to briefly describe Zariski spaces. So you just take like a Noetherian topological space where every irreducible closed set has a unique generic point. Okay, so this is the point for which the closure of the point is actually important. So you've seen examples of this. So here are some examples. So if you take R to be a commutative ring, then you can just take spec of R. Okay, so graduate school exercises actually show that this is actually a Noetherian topological space. It's actually a Zariski space too. So you can also look at graded, the graded spectrum. So you're just looking at graded prime ideals. And then if you have an algebraic group action, so acting as automorphisms on R, you can take this thing called G-proj. So you're basically taking graded prime ideals, which are G and then. And then there's a map from proj of R to G-proj of R. And you can just topologize G-proj of R using the quotient topology. Okay, so this isn't the invariant ring. This is a little bit different. All right, so that's Zariski spaces, and in Zariski spaces, we have just, a bunch of sets that we're going to be interested in. So we'll be interested in the collection of subsets, the closed sets, the irreducible sets. So let me just mention point 4, which is kind of important. So we say that a set is specialization closed if it's the union of closed sets. So this may be an arbitrary union. It need not just be a finite. So specialization closed set need not be closed. Okay. And then you want to look at the collection of specialization closed sets inside of X.
So what's an example? What do you think about when you're thinking of a specialization closed set that's not closed? What example should you have in mind?
Oh, I mean, you could just take a union of one, all of them closed. Infinite. Yeah, there are lots of examples. Okay.
What's an example of a set that's not special? So if you have like an open set, you guess you can't make that up. Like so you can a line throughout the origin.
Yeah.
I guess you can't make that as an arbitrary union closed set. I guess it's kind of.
Yeah, I don't think you could. Maybe.
I guess maybe not in the whole thing itself.
Right.
Something.
Right. So it turns out that this is a really good notion because you're able to classify ideals using specialization closed sets. So you may not be able to do things just with closed sets, but you actually need a little bit more of an enhancement. We'll see why this is important in a second. Okay, so we have monoidal triangulated categories, and then we have the topological space. And now I have to get from one to the other. All right, so to get from one to the other, I need an assignment. And this is called a support data. So support data satisfy certain axioms. They're axioms sort of natural with respect to the triangulated structure and also the tensor structure too. So basically, you want like the zero object to go to the empty set, the unit object to go to the whole thing. You want it to respect direct sums. You want it to respect the shift. You want it to sort of respect distinguished triangles. And then you want it to respect the tensor structure. And let me just mention, like in these axioms, there's S phi, which is a strong support data. And so this axiom is really for the complete prime ideals. And then WS is sort of for the prime ideals. So so you can sort of use one support data theory or another support data theory, depending on whether you're working with the completely prime spectrum or the prime spectrum. Okay, so this kind of looks a lot like support variety theory for like finite groups. And in fact, we also need two other properties which actually do come from finite group cohomology. So you need what's called the faithfulness property. So the way we can think about the faithfulness property is that it detects, the support sort of detects projectivity. So these aren't part of the axioms of support data, but we're going to need to assume these things for the support data to sort of classify. All right, so so we have this faithfulness property. So the support actually detects projective objects or zero objects. And also we have this realization property. So if I take any closed set, then I can realize it as a support of some object or some object, which is compact. Okay, so we've sort of got three things going. We have the tensor triangulated category, the monoidal triangulated category. We have this Zariski space. We have things that transport between tensor triangulated categories and Zariski spaces, but we need it to all sort of fit together. And so when we were studying this, we wanted a recipe. I guess that's the way to describe it. I mean, like Brian John and our representation theorists, And we wanted to actually give a recipe for computing the Balmer spectrum. And this recipe actually allows you to compute the Balmer spectrum, and it allows you to do a little bit more too. It allows you to classify thick tensor ideals in the compact part of the category. Okay. So let me see how this works. So, so first of all, you need a monoidal triangulated category, which is compactly generated. Right? So it's sort of generated by the finite objects, finite dimensional objects. And then you need a candidate. So you sort of find some candidate which might work. And so that's the Zariski space you want. And then you need an assignment which takes elements in your category to subsets of X, okay? And you want it to satisfy, certain properties, including S7 and S8. And once you have this support data, you can actually cook up an assignment. So you can actually take an ideal and you can assign to it a specialization close set by just doing sort of the most natural thing. You just take all elements in an ideal and apply the support to it. So this could be an infinite union, and it's some close infinite union of closed sets. So it's specialization closed. And then on the other hand, you can actually take a closed set and then assign to it a or specialization closed set, and you can assign to it an ideal, right? And this ideal is sort of defined. Okay, so you can actually show it's an ideal. A pretty easy exercise. So in order to make sure that this is a one-to-one assignment, you have to show that when you take the composition one way and you take the composition the other way, you get the identity. And that's not so easy. So in order to do that, you actually need some deep results of Mike Hopkins and Amnon Niemann to do this. So there's some sort of basic, some really deep mathematics which goes into this, which actually comes from homotopy theory. So, so at first this theorem looks kind of innocuous, but you really need some high-powered machinery to actually prove this theorem. And once you actually prove this theorem and you have things in place, you can actually, this set X actually identifies with the Balmer spectrum. Sorry, I can't hear.
What is that case supposed to be?
Oh, it's the compact objects. They're like the finite dimensional objects. So this is a good question. So no. KC. So for example, you could take like you could take the derived category, and you could take the perfect complex. And the derived category is actually compactly generated with the perfect complexes. Okay, so the answer is even though you're doing stuff just for the compact part, which you're pointing out something very important, you actually need the infinitely generated stuff too. Okay. Yeah, you really do need the infinitely generated. You can't just work in the compact world. You have to work in the bigger sense. Okay, all right, so that's fine and dandy, but so let me actually kind of recap things first before I go into some examples. All right, so here's the recap here. So we have these three things going on. We have the monoidal triangulated category, we have the Zariski space, and we have the support data sort of transporting this from one to the other. All right, so on my notes, I said pause, stop for questions. So at this point, it's actually a good point to pause for a second. If you have questions, please go ahead and ask. Any questions from the live audience? Questions from the Zoom audience?
Just to check, you need the support data to set up the sequence categories on the previous slide.
the equivalence of categories.
Or I guess between the big tensor ideals.
Let me go back and try to answer your question. Yeah, so you need the support data to get this homeomorphism.
I see.
Yeah. This support data is actually used to construct the homeomorphism. Yeah. And it's used to just construct, this is just a bijection. That's all. This one up here is just a bijection. This is actually more, this is actually probably.
I guess like depends on the support data though.
Well, yeah, neither side depends on the support data, but in order to get the homeomorphism, you need the support. Okay, good. Other questions?
So I'm just thinking like what is the definition of this this case. So like you were asking like one was like for the monodal input and so like
Oh, sorry. I'm going to answer. This is the second part of the talk. Okay. There you go. Yeah. So at first, I'm getting, well, can you actually compute this? And so what I'm going to do next is I'm going to do some examples where you can actually find this x. Okay, and it's quite natural too. That's a good question. Yeah. Good. All right. Any more questions? All right. So let's move on to some examples here. All right, so you can take G. G can be a finite group or a finite group scheme. And as we know, you can take the group cohomology or the cohomology from the group scheme, and this is just X to the trivial module itself. So this is the cohomology ring. People around here have studied this for many, many years. And so it turns out that the cohomology ring is really central to understanding the representation theory, or at least the tensor triangular geometry. So again, what you do is you take the stable module category for the finite group scheme, and then your X here is the projectivization of the spectrum of the cohomology ring. So it turns out that the cohomology ring is finitely generated. And so you can actually take the prime ideals in there and take the graded prime ideals. And so now your support data will just be the support variety theory. So if you look at WM, you just take all the prime ideals such that when you localize the cohomology of M with itself, you don't get zero. So this is the standard support variety theory. And it turns out that that does the job.
But I thought in support variety theory, you only got the inclusion of like these sets. Like when you did that support data, you had the two sets being equal. So I thought like you had the support, B tensor, the supported B tensor W was like contained in the supported support W or something like that. But there's some issue with the cohomology support that I'm sure you've gotten around this, but my vague memory of this was that there was some kind of you had only inclusion of the support data to get the equality.
No, this one's okay because it actually satisfies the tensor product properties. So this actually does the job.
Okay, I thought there was, wasn't there, am I misremembering, wasn't there something where the tensor product property was hard in some, or it wasn't?
Yeah. So in this case, it's okay. This was actually proved by like 300, but so in this case, the tensor product property is fine. Everything's good. There are cases where we have to be careful. Okay, but this one is okay. All right. So this has been verified and it's been known. Okay, so it turns out that the thick tensor ideals are in one-to-one correspondence with the specialization closed sets. And it turns out that the categorical spectrum or the Balmer spectrum identifies with the projectivization of the spectrum of the cohomology ring. Okay, so the cohomology ring actually identifies with Balmer spectrum. Very nice. Okay, so here's another example. So let's say you take a commutative Noetherian ring, and you want to actually find the categorical spectrum for DB perf Balmer. Right? And so the candidate here is just spec of the ring. So the idea is that this is sort of a recovery theorem. Maybe this was first through the Thomas. And so the idea is that you want to realize the spec of a ring as a categorical spectrum. And so you can actually define a support theory which actually works. So you take the complex and you just look at all prime ideals, which when you localize the homology of the complex, it's not equal to 0. Okay, so this support data actually works. And it turns out that the thick tensor ideals are in 1-1 correspondence with specialization closed sets inside a spec of R. And the Balmer spectrum, in this case, identifies with the spectrum of the ring. Okay, so it's a very nice picture for commutative and Noetherian rings. I'm interested in, like, suppose you don't have something which is commutative. Let's say you have a non-commutative Noetherian ring. Is there a theorem out there which actually realizes the spectrum in that case? And I actually don't know the answer. I think that's an open question. And it's kind of an interesting question, too, to try to extend this to the non-commutative situation. All right. Now, it turns out that when you take a situation where you don't have commutativity of the tensor product, you can actually still get some information. So I haven't defined what's called a quasi-support datum, but it's a support datum which has weaker conditions than a regular support datum. And you also need what's called assumption YY, which I'm not going to say what it is. But this sort of involves these localization factors and properties of these localization factors. So let's just take that as sort of a black box. So in this case, the finite dimensional Hopf-algebras, you can actually, if you assume the finite generation, then you can actually get a bijection between thick right ideals of the stable module category and specialization closed sets inside the projectivization of the homology. So this looks kind of like the finite group scheme situation. In the finite group scheme situation, the tensor product is commutative. So this sort of falls. That's a special case of this theorem. So one of the big things is what happens in general for finite dimensional Hopf-algebras. Can you compute the Balmer spectrum in that case? And so what I'll do is at the end of the talk, I'll touch on that a little bit. Okay. Now what I'll do is I will mention a more specific situation. All right, so some of you are probably familiar with this part of the talk. More familiar than I am with this part of the talk. So, so anyway, so we'll actually look at quantum groups. And so G is a complex simple Lie algebra, and U zeta G will be the small quantum group. Now, in 1993, Ginsburg and Kumar actually proved what the cohomology ring is for the small quantum group. So it turns out the odd degree cohomology is 0. And I'm assuming that L is bigger than the Cox ring over here. And if you take the even part of the cohomology ring, it identifies with the ring of regular functions on the nilpotent coordinate algebra. Okay, so there's a very nice description of this. I mean, the paper is a really beautiful paper. It actually extends a lot of the work that Friedlander and Partial did for the first Frobenius kernel. So they actually did the computation for the first Frobenius kernel first, and then Ginsburg and Kumar did this later on for the small quantum. Okay, now with cohomology, there's a naive functor. Okay, so if you take a module, you can look at the cohomology of that module, and then you can actually get an action of U zeta G of C on this cohomology. So it takes U zeta G modules to graded modules over this cohomology ring, which identifies with the coordinate algebra in the nilpotent cone. So you can think of this as a G equivariant coherent sheet for the nilpotent cone. Okay, so this is what Ginsburg and Kumar in their paper called the naive functor. All right. Now, about 10 years later, Arkhipov, Bezirkov, and Ginsburg were able to sort of soup up this functor, and they were able to prove this equivalence of derived categories. All right, so this equivalence establishes connections between the principal block for the big quantum group and root unity. Again, I'm assuming that L is bigger than H. G cross C star equivariant coherent sheets on the Springer resolution and perverse sheets on the root cross one and Langland's group. So there's a lot of words. You guys probably understand everything. So. All right, so so the point is that within this setup, though, the cohomology is really important. And so the computation of the cohomology ring actually turns out to be quite important for this equivalence of derived categories. And because of that connection here, you're able to say a few things. So the first thing is Bezirkov actually used this ABG equivalence to compute the support varieties of tilting modules. Okay, so you can define tilting modules for the larger quantum group and restrict them down to smaller quantum group, and you can compute the support varieties of these. And this involves looking at the closure of nilpotent orbits. And then there's some really beautiful representation theory that actually comes out of this too. This ABG equivalence yields a second proof of the Lustig character formula, i.e. the dimensions of simple U zeta G modules were L bigger than H. Yeah, the first proof was due to Kaishima Lustig and Kashiwara and Thomas Sutton. And then you can actually do X computations with this too. You can actually compute the X between two irreducible representations for regular hyperplanes. And the X are given by looking at products of Kaishima Lustig polynomials. Okay, so where does the tensor triangular geometry sort of fit into this? Well, this is what we proved. So we proved that if you take the large quantum group, okay, so it's U zeta G. So what you do is you take the Lustig ZV, the inverse form, you specialize it at the root of unity. Okay, so this is an infinite dimensional algebra, this U zeta G. Now, the nice thing about this big U zeta G is you have a Steinberg representation, and it's actually projective and injective for this category. So because of the existence of the Steinberg representation, you could form this stable module category in that sense. So it makes sense to actually try to understand the Balmer spectrum for this stable module category. And the smaller stable module category, namely the ones with finite dimensional modules. And so when you apply this machinery and also some really kind of complicated techniques, you get a correspondence between thick tensor ideals and specialization closed sets for this stack portion over here. So you take the spec of C of M, and you take the G invariant prime ideals inside of it. Okay? And then it turns out that that X identifies the Balmer spectrum. So what this shows is that for quantum groups, the tensor triangular geometry reveals the nilpotent cone. And so the nilpotent cone is actually built in to the tensor structure for quantum groups.
But now, from my perspective, this I don't really understand that see that because if you're looking at G invariant prime ideals, there's only going to be finitely many G invariant prime ideals in C of that, I guess.
That's right.
So that's a finite set.
That's correct.
There's only finitely many big tensor ideals in KMC.
That's a very good observation. Now, I'll say that next. And actually, that's the sort of surprising thing about this. So like with the least superalgebra case, you can get infinitely many prime ideals. But here you only get finite. So that's a little bit surprising because, you know, at first you would think, well, let me say it this way. So there's this theorem by Ostring, which looks at the category tilting modules and tensor ideals inside the category tilting modules. And so Ostring shows that when you look at that abelian category, then you get finitely many tensor ideals. And they're in bijective correspondence with no coordinates. And so it turns out that in this situation, you know, you could have like wild representation theory, and you have lots and lots of models for U zeta G. But you only have finitely many thick tensor ideals in this case. Just like with the tilting module situation. It's a little bit surprising, but maybe for people who know that tilting modules are very close to the category itself, maybe it's not so surprising. Okay. All right. So this is a summary of the proof. I'm not going to go over this. I mean, I think I have better things to say after this. So the point is that you need to reduce things down to U zeta B, and then you use some techniques involving the associated gradient, for example. And then you have to use Morka, Benson, Erdmann, Holloway to relate supports in the associated gradient to supports for a quantum complete intersection. And then you have to keep track of things pretty carefully. And once you actually keep track of things carefully, you can apply Morka, Benson, and Krause to actually finish the job. All right, now what about in the abelian category? Well, you can sort of pull things back. And this is what sort of Bill was alluding to. So if you want to just look at thick tensor ideals in mod U zeta G. Okay, so this is just the abelian category. It's not triangulated category. Then you can use the previous result to show that bijection between thick tensor ideals and G stable closed sets inside the Norfolk Hall. And so if you have non-zero thick prime tensor ideals inside of the bijective correspondence with Norfolk. So in particular, there are only finitely many G stable closed sets inside of that. So therefore, there are only like finitely many thick tensor ideals inside of U zeta G. Okay. All right. So it turns out that with this classification, so with this quasi support data, we didn't assume the tensor product property holds. Okay, the quasi support data sort of just assumes that you have one inclusion holding. And then we're actually able to work with that and then get the classification. And then it turns out once you have the classification, you can sort of prove that the tensor product theorem actually does it. Okay, so we actually proved that whenever you take two modules inside of the big quantum group, you take their tensor product and it's the intersection of supports. Okay, so we did not assume that at the start. This had to be derived later on. And if you want to work on an open problem, then if you take just arbitrary modules for the small quantum group, so the small quantum group sits inside the large quantum group, does the tensor product theorem actually hold in that situation? Okay, so this question is still an open problem. We think it's going to be true, but no proof has arisen so far. Okay, so I would like to sort of conclude the talk by what we're doing currently. So one of the sort of hot topics now is to actually understand tensor categories. So tensor categories are a little more general than monoidal categories. So you basically have a monoidal abelian category that's rigid and has finitely many objects, plus some other axioms. So this finite tensor category actually generalizes the category of finite dimensional representations for a finite dimensional Hopf-algebra. Okay? And so it turns out that for the case when the finite dimensional Hopf-algebra is co-commutative, then this conjecture is true. So that was a theorem of Friedlander and Sussland, pretty famous theorem that was proved in 1995, which took quite a while to actually establish. So for co-commutative Hopf-algebras, this conjecture that I mentioned is actually true. When H is a finite dimensional Hopf-algebra, an arbitrary one, then we don't know the answer in general. And so Oestrich and so Eddendorf and Oestrich actually stated a conjecture in general for finite tensor categories. So they purport that number one, the cohomology ring for a finite tensor category should be finitely generated, and that if you take two modules in this finite tensor category, then x to mm is a finitely generated module. So this was mentioned in my Julia Plattner's talk last spring. Okay. Now, Julia also mentioned some work that that they did. So under the assumptions of finite generation, and they are actually able to develop a support theory, and this is much like the work that was started and developed by John Carlson back in the 1980s and 1990s. So they established a theory using these Carlson L-zeta modules. These turn out to be important building blocks in the theory. They have a connection to the complexity of modules. So the complexity was first due to John Alpern, and so they have an interpretation of the complexity via support varieties. I think this connectedness result was mentioned. So the connectedness of the projectivization of supports of indecomposable modules. And then there's a Carlson realization theorem that they were actually able to prove. So the Carlson realization theorem is like the realization axiom that I stated earlier for support data. Okay, so, oops. So let me mention what we're doing. So, so now what we're doing is we're studying thick tensor ideals in the Balmer spectrum for stable module categories for finite tensor categories. In particular, this includes all finite dimensional Hopf-algebras. We have some new ideas, and we're currently writing these new ideas up, and we hope the results will be out in the next month or so. Okay, so thank you very much, and my little advertisement. Okay.
So in your slide, you talked about the naive functor. So I didn't quite understand why that is the naive functor and what's the good functor. That was way back in the Kumar stuff.
Yeah, so probably Laura can probably answer this better than I can. But you need to actually, so this functor is only sort of at the module level. You need to sort of jack it up to the derived category level. And I think you need this sort of notion of what's called formality to actually do that. So it's actually in the Archibald Desert problem. Yeah, it's a non-trivial type of construction. Yeah, go ahead.
Yeah, this question there, when you were looking at the bijection between the notebook models.
Okay, let's see. Is it- Yeah. This one out. Yeah.
There. So you mentioned, like, for example, you use the fact that it's finite and then you put more to say something about finite ideas.
Right.
Has anyone looked into, like, specializing down to certain types of little orbits and saying more than that about this? Like, for example, I'm thinking, looking at like special little orbits as we did define.
That's a really good question. This is pretty coarse. Yeah, so I don't know the answer right off now. Whether you can use the more sort of specialized knowledge of things to get more specialized sort of information. So I don't know the answer. It'd be an interesting question for sure.
Well, you said treat these categories like rings. So one thing one likes to do with rings is put it together to make non-affine varieties.
Mhm.
So is there an analog of like putting these categories together to get some kind of thing that maybe isn't quite a category, but would be the analog of like a projective algebraic variety?
I actually don't know, but that's a really interesting question. It's sort of, well, this theory's been around for a fairly long time in some ways, but I mean, certain constructions are still being sort of developed from a categorical point of view.
Because you don't glue these things together, but it would be a category for something else.
Could be.
Because if it was a category, it would just be back to the
Right.
same thing again.
Yeah, so you have on one side you have these sort of module categories with a tensor product structure. On the other side you have these topological spaces. And it's still a little bit mysterious about how everything works.
Like another thing is like you say, like for example, well, the main thing you use in gluing rings and stuff is like the localization of a ring.
Mhm.
So is there an analog of the localization of rings? I mean, this kind of categorical language. If you had that, that's how you would glue things together. You can go into like open sets.
Yeah, let me think. I think Balmer has done some work on this, but I'm not sure exactly whether it's in the direction that you're mentioning. But he does, look at localizations within these categories.